So the next talk is by Dr. Venkata Raghavendra. So he is a scientist at the U.R. Rao Satellite Center at the Indian Space Research Organization, ISRO, Bengaluru. He received a bachelor's degree in mechanical engineering from University Visvesvaraya College of Engineering, Bengaluru in 1995 and master's degree in heat power engineering from the National Institute of Technology, Surathkal in 1998 and the PhD degree in mechanical engineering from the Indian Institute of Science, Bengaluru in 2020. His research focuses on heat transfer and thermal control of spacecrafts.
Yeah, thanks for inviting us to this workshop because we get very rare opportunity to interact with the academia people actually. And actually my talk was scheduled between 2 to 3 p.m. Today, but the launch is preponed. So, and I have been given 45 minutes time. So, we have to land onto the lunar surface within 45 minutes and your lunch is arranged on moon today. So, I have to hold back. Sorry for holding you back. And before starting, I would like to thank Professor Rishiraj because he has taken us from Earth to space. So, my job is reduced now. I have to take all of you from space to moon. Okay. Okay. My topic because I would like to give some introduction on spacecraft thermal management because then only you can appreciate what are all the challenges in reaching moon, then lunar environment, then challenges in reaching moon, and just a brief overview of Chandrayaan 3 thermal management because most of you by now will be knowing about Chandrayaan 3 more than us because lots of things are floating in social media. So, just a thermal management aspect I will cover. So, what is the objective of spacecraft thermal management? Because we have heard from yesterday the same objective to maintain the temperatures of all the subsystems within their actual acceptance limit during the launch phase and prior to launch phase when we are integrating the spacecraft and till end of mission life. The only difference is we do not have option of repairing if any anomaly happens. So, no servicing is possible as on date, maybe future it may be possible. So, we should be very precise in doing what we are doing. Then why thermal management? Because all these space electronics they depend on the performance of these electronics depend on device temperatures and a few power sources like solar panels, batteries, especially batteries it is talked about since yesterday, and some sensors, cameras and all they depend on the temperatures, and fluids like propellants, electrolytes in some spacecraft, coolants, they have to be prevented from freezing and boiling during operation. And naturally mechanical structures they are prone to thermal distortions if a large temperature gradient is there. So, we have to avoid thermal distortion, especially where we are using cameras and all because see we are in say 800 kilometer orbit or 35,880 kilometer orbit. When we are seeing Earth, even 0.001 degree deviation from the look angle, we will not be seeing where we are intended to see. Suppose we want to see India, just 0.001 degree will be much away from India. So, this stable platform is very essential because of so we have to avoid thermal distortions. And how do we do thermal management? Because as you know, in space we do not have convection because convection is by far the best mode of heat removal, but convection is missing and we have only conduction and radiation. So, basically thermal management is the heat is generated somewhere or accumulated somewhere. So, we have to transport it to heat sink. See, basically in space heat sink is space because space when it is not seeing an object kept in space, if it is not seeing sun, its temperature will be around 2.7 Kelvin. So, that is the sink for us. So, all this thermal management is just to transport the heat to the outer surface because we can radiate heat from outer surface only to space because the inside surface will not be having view to space. So, how to bring the heat from internal electronic packages where heat is generated or it is accumulated from other surroundings, and how to bring it to the outer surface is the challenge in spacecraft thermal management. So there are two ways generally we do this thermal management at two levels actually, subsystem level and system level. Subsystem level is like package. So packages, see we have to deal with the devices, components, and then PCBs, then package. So this is very important. So what we do package level thermal design and analysis, where we will assume that the base temperature of the package is restricted within a acceptance limit. Then next we will do spacecraft level thermal design, where we will ensure that the package base in the spacecraft level is maintained to that temperature. So if we are able to maintain the temperature of the electronics base, then it is taken care, all device and electronics temperatures are taken care. So this is basically achieved through energy balance, because finally thermal management is energy balance. So you take a control surface, how heat is generated in the control surface, how it is conducted from the surrounding control surface, that only we have to transport it to the sink. Okay. So for doing this, we will be using lots of thermal control elements like interface materials. We have different types of interface materials. Then we use heat spreaders, insulation blankets, then conductive isolators, surface finishes like different types of paints and all, coatings, tapes we use. Then it will be augmented with heaters. Wherever temperatures falls down, we use electrical heaters to increase the temperatures. Then finally we use thermal radiator. It is called OSR, it is optically solar reflector, because so it is a secondary surface mirror. What it does, when a load from sun comes onto the radiator, because spacecraft whenever it is in orbit, it will be seeing, some portion of the spacecraft will be seeing sun and some portion will be seeing deep space. So whenever it sees sun, the sun load will be entering into the spacecraft if you open the area for radiation. So this OSR, what it does, 10% of the load only in the visible range it is absorbed, and 80% of the load, whatever is there, heat is there inside in IR range, will be radiated out. So it is a beautiful phenomena, this OSR, which generally we don't use in ground applications, which will be used only in space applications. So all these are extensively used in the spacecraft. So this, as I told, it's basically a energy balance. The thermal management is energy balance. All the heat conducted from the control surface and also accumulated from the surrounding control surfaces, plus heat received through radiation from the surrounding control surfaces, and heat generated within the control volume, and then the external heat like heat load from the sun. Albedo load is the absorbed load, the sun load fallen onto the earth surface and absorbed back to the satellite. Or if it is an interplanetary mission, the planetary body, sun falls onto the planetary body and again comes back to the satellite. And earth shine load or moon shine load or any planet shine load is IR load due to its own temperature emitted by the planet and which is received by the spacecraft. And finally it will be subtracted by heat radiated to space. So this equals to energy stored, rate of energy storage. It determines, suppose energy is stored at every instant, energy storage increases, temperature increases, energy storage reduces, temperature falls down. And this again is formulated into equation as shown below. So these are some of the thermal control elements, because if you see spacecraft, you would have seen lot of images of the spacecraft. Whatever you see from outside, most of them are thermal control elements, because it may be a mirror like surface. It is a OSR actually, and this is a gold. Actually it is not gold, gold colored. It is a aluminum coated Kapton. It's a polyamide sheet, and that is a insulation blanket, then white paint, black paints. So most of the whatever you see from outside, they are all control elements, like quartzol blanket we use, foil heaters, tape heaters. This is OSR tiles. Then different types of tapes, heat pipes, and then thermal straps, like we use copper straps and pyrolytic graphite straps. We use heat shields. This is a spacecraft engine to ensure that the heat load from the plumes will not be seen by the spacecraft body. We will have a radiation isolators here, then spacers, temperature sensors to measure the temperature, thermal grease, and we use different types of thermal interface materials. One of them is thermal grease, otherwise we use thermal pads also we use, or compressible PGS we use. then different types of paints you can see there. So based on this, we develop a thermal mathematical model. It's a thermal mathematical model is developed using FEM technique. Generally, we use different space agencies use different tools. We use UGNX for that, and TMG is a thermal model generator, and it is solved using FDM technique. So we build the model. See, this is Cartosat 2 spacecraft model, Chandrayaan 3. This Mars orbiter mission model. So once we build the model, the analyzer will take care of solving the every node. It will solve for energy balance and temperatures will be obtained. So we give different boundary conditions for different mission phases, because any satellite, when it is like launch phase, it will have a different boundary conditions, and then post launch, when it is inside the nose cone or heat shield, it will have a different boundary conditions. When it reaches orbit, it will have different boundary conditions. So among all the phases, we identify worst hot or worst cold case, and then we will ensure that for the worst hot case, whether all temperatures are within the limits. Otherwise, we play with the thermal radiator area, and for worst cold case, we will see whether all temperatures are above the acceptance limit. If not, we will use more electrical heater power to ensure that temperatures are maintained. So then we validate these thermal models using tests. We do tests in package level also, and we do spacecraft level also. Generally, we will try to spacecraft levels. We will try to do thermal balance test. We will try to simulate space environment, like high vacuum we create, and the temperature also we simulate, and we will subject the spacecraft to harsh space environment, and we will do the test and validate our model. So this is just showing electronic package, how we, this is a solid model of an electronic, typical electronic package. This is how they are made to a meshing, and then this is how we solve and how the temperatures are mapped. So this is just a brief introduction about spacecraft thermal management. Now we will see lunar environment. This I will not cover entirely because shortage of time here. Only important thing is it just lists, because this is, most of you are aware the characteristics between Earth and Moon. Only important for a thermal engineer is see, Earth has a atmosphere, because of which even daytime or night time its average temperature is say around 15 to 20 degrees Celsius. But Moon is not like that. Moon doesn't have atmosphere, which is very challenging for a thermal engineer to maintain the spacecraft temperatures, because of the IR load emanating from the Moon surface to the spacecraft. See, it can go, this is actually in equator, it can be between 100 Kelvin to close to 400 Kelvin. When it is sunlit, it can be as high as 400 Kelvin. When it is not sunlit, it will be 100 Kelvin. And in a polar region, it will be further down. It can be as low as 20 to 30 Kelvin also, especially craters and all. It will never, it has not seen sun for millions of years, and temperatures can be 20 to 30 Kelvin also. So when it is the load is coming from the crater, the energy is so low that we have to design basically the thermal management such that we should take care of all these varying loads coming from the Moon surface, because say polar orbit means it will be passing through the poles also, and it will be passing through the equator also. So this, and the other thing is the IR load near equator, where it is sunlit, it will be as high as 1300 watts per meter square, but dark side, wherever it is not sunlit, it is 6 watts per meter square. See, this is IR load coming onto the thermal radiator. As I already told, thermal radiator, it has a property of solar absorptance of 10%, but in IR range it is 80%. That means when IR load is coming from Moon, it is like 80% of this 1300 watts per meter square will be absorbed. That means it is almost like multiple suns. See, one sun is 1400 watts per meter square flux coming from sun, but absorbing is only 10%. But here sun load is similar, your earth-chain load is similar, but absorbing is 8 times higher. 0.8 is the IR emittance for thermal radiator. This is also very challenging for any spacecraft orbiting around moon or for landing missions. This is some data from previous spacecraft from NASA actually. This is a Clementine spacecraft. They have very beautifully, though this spacecraft launched in 1994 and it was orbiting around moon only for 70 days, but within 70 days they have captured multiple temperatures at different locations, and till now this is being used by most of the spacefaring nations to design for the lunar missions. Though it was launched in 1994, and later we have from LRO, it is a lunar reconnaissance orbiter, that also has mapped Earth. You can see this is the dark side where sun is not there, it is very cool, it is very low temperature, and this is the equator. You can see at the equator zone, and where it is sunlit, it is very high, so close to 400 Kelvin. And other than this, for landing mission, for lander craft, another important thing is its surface characteristics, because unlike Earth, there is no atmosphere there, so there is a deposit of a layer of dust called fluff. It will be approximately 2 centimeter thick, and they are zagged and glass like, and they are electrostatically charged. Electrostatically charged means if they are clinging on to any surface, it will hold on to it, because there is no wind to take the dust away from the surface, and it has a optical property of very high solar absorptance of 0.87 and emittance of 0.97. So, due to this and also lower thermal capacity, the dust surface it heats and cools very fast actually, because there is no conduction, thermal conductivity also is very less, capacity also is very low. So, it cools very fast, and suppose if it gets accumulated onto the surface like thermal radiator and all, it will be very challenging to get the temperatures the way we designed and intended. Temperatures we may not get. So, this is the basically this is the measurement done on the equator, where they tell in the regolith below the dust the temperature variation is very high due to lower thermal conductivity of the regolith. So, they measured, this is a NASA spacecraft, they measured that it is almost 3 Kelvin per meter in the equator zone. But recently from Chandrayaan 3 we measured on the south pole, we measured, because since you are aware, Chandrayaan 3 was the first spacecraft to land onto the south pole of the moon. So, we have seen here that within 100 millimeter, because we had a chaste payload which drilled the surface for 100 mm, and within 50 millimeter we could see almost 50 degrees Celsius, within 100 millimeter 50 degrees Celsius temperature difference we could see. So, now we will come to challenges in lunar missions, how it is different from other earth orbiting missions. So, see, to reach moon there are multiple phases. The first phase is a launch phase, from launch till the first orbit. So, it is a launch phase where spacecraft will be inside the nose cone, it is called heat shield. So, it will have different environment there, because generally we design thermal management based on conduction and radiation, but here during launch or prior to launch we have convection also. So, next phase is earthbound phase. Here you can see we will be doing lots of maneuvers, and every maneuver will be increasing the orbit. So, this is just to get the advantage of gravity of the earth to propel the spacecraft. See, there are two ways of basically we need energy for spacecraft to reach any interplanetary body. Either you use fuel and get the acceleration, or you take advantage of the gravity of the earth and get the acceleration, so that with the minimum fuel consumption you can go away from the as far as possible from the earth. So, this is the earthbound phase. Then we have lunar translunar injection, because see this orbit rising at after certain orbits we rise the orbit such that its apogee, the elliptical, the farthest point in the ellipse will be almost similar to the distance between earth and moon. It is around 3.84 lakh kilometers. So, with this maneuver it will try to reach the moon, but its velocity will be escape as you know, earth's escape velocity is very high, but moon's is less. So, if you do not apply brake, it will move away from the moon. But here what we do, we will apply brake. It is a retro firing we call. We will rotate the spacecraft and they fire the engine so that its speed velocity reduces drastically and it will be captured by moon's gravity. So once it is captured by moon's gravity, we will have multiple orbits. So it will have a longer elliptical orbit in the beginning, and then every stage we apply brake, and then we will reach the polar orbit 100 by 100 kilometer per or around 100 to 150 kilometer orbit we reach. And then here where the lander and orbiter craft, they separate, because orbiter's main objective is to orbit around the moon, but lander has to land on the moon. So it will be separated here, and from there we have again lander craft will be again further deorbited to lower elliptical orbit, say 100 by 20 kilometer or 100 by 50 kilometer, and from that distance it will land onto the lunar surface. That is the lunar descent phase. This is a very important phase, though it is only for 18 to 20 minutes. The most challenge for thermal engineer is in this phase only. And next is lunar surface. So once it is touched down, we have lots of other challenges for thermal management, which I will address in subsequent slides. Basically we have to, thermal designer has to ensure that in all these phases temperatures of the spacecraft and its subsystems are maintained. So now we will start one by one what are all the major challenges during every phase. So first is launch phase. As I told, initially when spacecraft is inside the heat shield, it will have a natural convection environment, and then later once spacecraft starts moving, it's accelerated away from the earth, then heat shield will be opened. The moment heat shield will be opened, the spacecraft will be exposed to aerodynamic heat flux. So thermal designer has to take care of the heat flux coming from the aerodynamic drag, and then we have to design such that none of the spacecraft elements crosses the temperatures. And next, once heat shield is opened, we have heat load from sun and earth also. See, as long as heat shield is there, it is protected from external loads, but the moment heat shield is opened, it will be seeing sun as well as earth also. But in this phase, the internal generation, that is the waste heat generated from the electronic packages, are minimum, because we will not have any control electronics operating in the system. Only transmitter and receiver will be on, and no payload or no scientific instruments will be operated in this phase. So heat generation inside the spacecraft is minimum, and external appendages also will be in stored condition, like solar panels or some instruments, antennas and all, they will all be in stored condition. So here the view factor of the spacecraft elements to space will be different as compared to in orbit condition, where all these appendages will be deployed. And the next thing is heat pipe, whether heat pipes will function during ascent, because see, one thing about heat pipe is it works on gravity, but only thing, there is a constraint. If you keep it exactly vertical and heat from the top, it will not work. Though it is we tell heat pipes compared to thermosiphon, it works on gravity, but there is a static wicking height, that constraint is there. To that tilt only it will work. The moment it becomes vertical or more than tilt is more that static wicking height, if you heat from the top, the liquid becomes vapor, and vapor becomes liquid at the top, and it moves towards the bottom. Once liquid moves towards the bottom, the gravity will not allow it to rise, so the liquid cannot come back. So here also similar thing, though gravity effect is not there, but there is an acceleration. So if heat pipe is in the acceleration direction, and heating is at towards the other direction, then heat pipe will work. Otherwise all liquid will go, and suppose we are heating from the other side in the acceleration direction, all liquid will be away from the acceleration direction, so heat pipe will not work. So this also we have to take care during our design. So this just to show this is the onboard camera view of Chandrayaan 3. This image is taken from the launch vehicle. See, you can see the moment it is ejected, how it is exposed to sun load and earth loads. You can see the brightness, increase in brightness after it is ejected to space. So then once a spacecraft is in orbit, we will be doing lot of maneuvers, because now we have to stabilize the spacecraft in the Earth's orbit, and then we have to increase the orbit, we have to raise the orbit height with every orbit. So lots of maneuvers are there, and these maneuvers will have spacecraft change in spacecraft attitude, because spacecraft will be oriented in certain direction. Then the load coming from Earth and Sun will be different. It keeps changing during the maneuvers. And then here, once spacecraft is in orbit, few of the packages, electronic packages will be switched on, like control packages will be switched on. So the internal heat dissipation also increases, and then there will be variation in eclipse period also, though eclipse period remains same around for all these orbits. But as we move away from the Earth for the larger orbital this one, the orbit period is more, but eclipse duration is same. So the percentage of eclipse or shadowed region in an orbit keeps decreasing with every orbit maneuver. Then other than that, we have, this is a common problem for most of the spacecraft, we have a Van Allen belt from around 640 to 58,000 kilometer. So all components which we use in spacecraft should be radiation hardened, otherwise components will not work. And especially for interplanetary missions, the thickness of the package walls will be higher as compared to the other spacecraft, so that see again the thermal heat transfer path or the thermal resistance changes for the missions like lunar missions. So this also we have to account. So once we are in Earth's orbit, here as I told, the last maneuver will be such that it will start moving towards moon, and once it is about to reach moon, that is not yet reached moon, it is still in translunar injection phase. There we don't have external load from Earth also, and we don't have from moon also, because it will be between Earth and moon. So there only sun load will be there, and after that it will be captured by moon. Then we will start seeing heat load from moon also. So both from moon and sun load will be there. Then this load also, especially moon's load, it will be, variation is extreme, because see, whenever spacecraft comes very close to moon, then lot of IR heating will be there, and albedo heating also will be there. When spacecraft moves away from the moons in the elliptical orbit, the load decreases drastically. So then once we are in the polar orbit, orbiter craft and lander separates, then again view factor of, because whenever orbiter and lander are together, it will have different view factor to space. The components or the faces of the spacecraft will have different view factors. Lander will be blocked by orbiter, orbiter will be blocked by lander. But once they separate, then view factor to space, the radiation mechanism, the area of radiation will increase, and there also temperature changes will happen. And here once lander craft is separated from the orbiter craft, again many packages, electronic packages in lander also will become on, because now because they are now totally two different spacecraft. Earlier orbiter craft was ensuring that all controlling this orbiter craft only will do. Now lander has to do its own controlling, and orbiter has to do its own controlling. So again we will have higher heat dissipation in the lander craft also. And the other important change is, see, whenever we reach interplanetary bodies, we have to transmit the signal from here or receive the signal from the spacecraft using deep space network. Since the distance is very huge, lot of power will be radiated, because to send the signal from Earth to almost 4 lakh kilometers, the more power is pumped out of the spacecraft, so that lot of input power also is higher. Because of this, the heat dissipation of the electronic package, especially transmitters and receivers, will have higher dissipation as compared to Earth orbiting spacecrafts. Now power descent, as I told, this is the most crucial phase for even thermal engineers, because this is the phase, though it is only for 18 to 20 minutes, but all the electronic packages will be on here. Your navigation, guidance, control, cameras, everything will be made on in this phase. So lots of heat generation is there, and apart from that, see, we have to apply brake. It will be around 30,000 kilometer per hour speed it will be approaching moon. So we have to make it 0 kilometer per hour. So a lot of braking happens. The braking happens unlike Martian surface or Venus. Here we don't have atmosphere. We cannot use aerodynamic drag for braking. So we have to use engines only. So once we have multiple engines in lunar missions. All will be simultaneously fired. Because of that, that plume will get mixed and upward draft will be there. That plume will try to reach the satellite surface. Because of that, lots of heat, especially in Chandrayaan 3, we have seen up to 31 kilowatts per meter square of heat flux was seen by the spacecraft. So we should design a very good thermal protection system. Otherwise, the component which are exposed to plumes, upward plumes, will almost melt. So that also is a big challenge. And next is, see, when your solar panel is designed for certain electrical power generation, but here what happens, since all electronic packages are on, so we have less availability of electrical power or heater operations. So we cannot, if temperature, because at one side it may be seeing moon and sun, but other side it may be seeing deep space. So I don't have the flexibility of switching on the heaters at my wish. So that also is constrained during power descent phase. So next is touchdown phase. This is very important because it was for us it was first time for ISRO that lunar descent. So a lot of dust also will be there. So they may go and settle on thermal radiator, or they may go and settle on solar panel. If solar panel it settles, then power generation is minimum, then heater power will not be available. And other thing is, it may go and settle on camera also. So all these things, the design should be such that there should be minimum dust settlement on the satellite surface. So only one good thing is here, unlike Martian surface, here there is no atmosphere. So dust, if it rises, it will settle vertically down. So it will not, horizontal movement is not there. So these legs and engines are located such that during its touchdown, it will be, the dust will move away in 15-degree angle. So once dust rises like this, then it will settle there only. So it will not come onto the lunar surface. So this design also was carried out to ensure that dust settlement is minimum. And next is, see, we intend to land the lander on a particular orientation, so that sun will come, because we have only 14 days of sunshine on the lunar surface and 14 earth days is night. So to have maximum utilization of the sun, we will ensure, we will design that lander will land like this. So accordingly, thermal also will take care of sun, because sun will relatively move with the time. So we'll design such that on this surface first sun will see, and after a few days it will start seeing in this surface like that. But by chance, if lander rotates with the angle, or if it lands on a surface where local slope is higher, then our calculations will go wrong, because whatever absorbed sun load or moon load we consider, it will not be there after landing. So that is also another critical thing. And next is, due to very low thermal conductivity, if you see this zone, wherever shadowed zone is there, temperature will be as low as 150 Kelvin. But wherever sunlit is there, there is a drastic difference across the shadow boundary. Here temperatures will be around 300 Kelvin. So large difference will be there, and the load from shadowed region onto the lander and load from the sunlit region, they are totally different. And if boulder is there, because especially when pole landing, if boulder is there, it will have a parallel shadow. Even if at 1 kilometer away some big mountain is there, it can be shadowed for longer days. So all these things we have to account for the thermal design. So basically all these things will affect the radiatory area, because the radiatory area, in the presence of sun, its effectiveness will be different. In the absence of sun load, its effectiveness will be different. And here, after landing, your control, navigation, guidance, all these electronic packages will be turned off. Only transmitter, receiver and scientific instruments only will be turned on. So heat generated within the spacecraft also is minimum. And the other thing is functioning of heat pipes. Again, heat pipes, gravity is there, though it is 1/6 of Earth's gravity, but again we have to ensure that the orientation of the heat pipe is such that it works the way we want. So if it is any heat pipe is there, we have to ensure that heat source or heat load will enter the heat pipe from the bottom, so that it will work like a heat pipe. So that orientation also is very critical, but it is very challenging because we cannot ensure for all the electronic packages the heat will be from the bottom only, is not possible. So we had multiple heat pipes. Suppose see, I will design like this and the slope is like this, then this heat pipe may not work, or slope is like this set of heat pipes will not work. So we have designed such that the multiple heat pipes are used in L shape, and suppose whatever is the orientation, at least one set of heat pipes will work. That is how we designed the heat pipe network, as Professor Marco said, because basically the major thermal control element in spacecraft, especially wherever the high heat carrying capacity is there we have to use the heat pipe network. So we had a very typical heat pipe network for lunar mission. And the next challenge is lunar night survivability. Anyhow, we have studied a lot, but we have studied with because finally we need energy. We have to store energy, and then we have to ensure that the temperatures are maintained above their operating temperatures. But 14 days is too long time that all temperatures of the packages will fall below 100 Kelvin. So to maintain it say around 250 Kelvin is a real challenge. And we tried whether we can take larger batteries or some chemical we will take, and exothermic reaction, it will release heat and it will maintain the temperatures. But finally we found that the either battery or chemicals, that volume and quantity is so huge that it will be like a big apartment size. We have to carry the battery to sustain or to give power continuously for 14 days. The only option is nuclear source. So, but in India we do not have plutonium source for we use only for civilian applications. We went to DAE BARC and we told we need around 30 grams of plutonium 238, and they said our production capacity is a few micrograms per year, and it takes hundreds of years to produce this much. And then okay, we finally carried, we thought instead of plutonium we will use americium. So we carried 2 RHUs in the propulsion module just as a demonstration, because we wanted to work out the feasibility of using radioactive radioactive isotope heating unit for the interplanetary missions. We carried 2 RHUs and it was successful, and it only generates 1 watt each. So we have done the instrumentation such that to ensure that it is releasing 1 watt, and it is not performance is not diminishing with the time. So till date almost 4-5 months it is releasing 1 watt of heat, but it is in the orbiter. So now we will take up, I will not okay, due to certain restrictions I cannot give finer details of Chandrayaan 3 thermal management, just I will cover a brief overview. So this is a spacecraft Chandrayaan 3, like Chandrayaan 2 was a composite of 3 modules. This is in Chandrayaan 2 it was called orbiter module, because we carried some 8 science instruments in orbiter also, but here its objective was to take a lander to the lunar surface. It had no other objective of science. So that is why in Chandrayaan 3 it is called propulsion module, but later we added one scientific instrument called SHAPE. I will come to that. And after that we had a lander module above that, and inside lander we had a rover, because one of the vertical panels of the lander, it will open after lander is landed, and rover will come out. So this is the exposed view of propulsion module or this lander, and this is a rover. So lander and rover had carried science instruments. So again same this one different views. So you can see all star sensors, and this is the payload on the orbiter propulsion module. This is the antenna. These are all the external appendages. Even in lander you can see sensors, and LRA is a payload from NASA, and LDV is a sensor, all developed by ISRO only, altimeters. Then engines, you can see we had 4 800 Newton throttleable engines. These are the engines which were used to apply brake when we were approaching moon. So the mission objective for Chandrayaan 3 was safe and soft landing, and the roving of the rover on the moon surface, and we had few in situ science experiments. So this Chandrayaan 3 was launched using LVM-3, and it has put the spacecraft into exactly very precise orbit of 170 km by 36,500 km ellipse, and then spacecraft mass was around 3900 kilograms, out of which propulsion module had around 2000 plus kg, and lander had 1750 kg. So you can see how much fuel is required. See, this is the total weight of the propulsion module, out of which dry weight of propulsion module is around 450 kg only, and we had to take around 1700 kg of fuel to take the Chandrayaan 3 to the lander. And in lander also you can see out of 1750 dry mass of the lander is 708, we needed around 1000 plus kg of fuel to apply brake to ensure that we land safely and softly onto the lunar surface. So this is this spacecraft in vibration bench. So we had to simulate vibration because it has to withstand all launch time vibrations also. So lander had 4 payloads actually. Chaste is one which has done thermal experiments. I had shown the plot earlier. So this had a probe which drilled inside the lunar surface for 100 millimeter, and it has estimated the temperature and thermal conductivity of the regolith. And the Ramba is a Langmuir probe. This also for plasma studies on the near surface of the moon. And then ILSA is the seismic activity, because like Earth we have seismic activities on lunar surface also. Actually we have got a very few very interesting signs from this. Maybe some papers will come out in due course of time, which we could not tell is it because of any something moving around the lander, or it is really because of the seismic activity. We have seen few vibrations using this instrument. And this is LRA. This is a very passive payload. It's basically it's a laser retro reflector. This will be used in future also. Any orbiter it can send the laser signal and get back the reflection, and it will tell what is the actual location of the lander. And rover carried 2 important payloads. One is LIPS, it is laser based spectroscope, and other is APEX, it is X-ray alpha particle X-ray spectroscope. These 2 instruments together they found the interesting fact that apart from other elements we have sulfur also on the south pole. This was not detected earlier by any other space moon based spacecraft. And then propulsion module has a shape payload. It is like we are planning to have exoplanets satellites in the future. We want to see whether like Earth anywhere else life is there. So how to find out, because before going there or without going there, how to find out it is a Earth like planet. So this payload has though it is in the moon's orbit, anyhow now the propulsion module is in Earth's orbit only, but it will be looking always towards Earth. So it is capturing the signature of Earth because of hydrogen, because of oxygen presence, what characteristics we get. So these are all the maps which the data we are generating. Based on this data, future we will try to search for another planet with similar signatures. Then we will come to know here hydrogen is abundant, nitrogen is abundant, oxygen is abundant, so that we can see that there is a scope, or there is a life in other planets also. So this is the payload for that. So this is the mission profile. Anyway, I explained this. Landing we had 3 major phases: rough braking phase, and then attitude hold phase. This is just to see the landing site, any hazards are there, and also to we wanted to stop somewhere and see how we are going, whether till now we have come properly, and future how much distance is there for the landing site. So this is only few seconds, some 3-4 seconds we have done that study, and then we have come to hovering phase. We had 2 hovering phase and then vertical descent. And primary we had 2 landing sites. Suppose on that particular day, August 23rd, if we are not able to start landing descent, then we had an alternate site at 69.49 degrees south and different longitude. So we could start on the same day and we could land. Actually 69.36 degrees south was the intended latitude. We landed at 69.37 degrees south latitude. And coming to the propulsion module, which is an orbiter, we have different again external load will keep varying. We have noon midnight orbit and dawn dusk orbit. See, you can see this Earth and Moon, they will orbit around Sun. And suppose this is a polar orbit, these are all, this line shows polar orbit. So you can see here when it comes, it is noon midnight. When satellite is orbiting like this, the moon will have earth sunlit in this zone and non-sunlit this zone. So that's why it is called noon midnight orbit. And when it comes to that position, it is a dawn dusk orbit. You can see it is like always 6 a.m. 6 p.m. The sun load on the sub lunar point is always same. So this will have different external loads coming onto the spacecraft. So we have to handle this variation in load also in the thermal design. So this is just a gist of because as I told, we have used multiple thermal control elements like OSR, MLI, heat pipes, different types of paints. It just gives in propulsion module, lander and rover like how many electronic packages are there, what was the peak heat dissipation, how much OSR area used, then number of heat pipes, heaters, temperature sensors, and what is the say out of almost 3900 kg was the total Chandrayaan 3 mass. But thermal control element masses are only 42 plus 56 plus 1.6 kg. It's hardly around 2 to 3% of the total mass. So based on all the inputs and different boundary conditions, we have developed independent thermal mathematical models for propulsion module, lander and rover, and then we integrated them together, and we have run the cases for integrated model also. And thermal analysis were carried for all the possible cases in the mission, starting from the launch phase till post landing case onto the lunar surface. And we have done extensive testing to validate this model to ensure that at any cost we will be within the accepted temperature for all the packages in the spacecraft. So I will just go through 2 minutes. Just I will show the some. I think most of you would have seen this in internet. This is in Sriharikota. The satellite Chandrayaan 3 satellite was being moved on to the launch vehicle adapter and heat shield. You can see once it is sitting on the adapter, then heat shield will be closed. And this Chandrayaan 3 ready for launch. This is the launch event. You can see how nicely, how smoothly launch vehicle is lifting off with minimum vibration or with minimum disturbance. This actually has, this launch has saved us almost more than 100 kg of fuel for orbiter, and even lander also. Landing was so precise. After landing also we had almost 50 to 60 kg of excess fuel, because of which we could do hopping experiment also. For sample return, we just wanted to see what is the resistance to lift off from lunar surface. We have done a hopping experiment also. So these are all different timelines for the events. We have the launch was on 14th July, and then TLI was on 31st July. We reached moon on 5th August. Then multiple lunar maneuvers, and finally spacecraft was separated on 17th August, lander and propulsion module. Then we started deboost for lander from 100 by 100 to 100 by 30 kilometer orbit on 17th, 18th and 19th. Finally we landed on 23rd June. This will show the camera image of the lander imager camera during descent. The last, actually it is taken over 18 minutes, but it is compressed to less than a minute. So you can see the braking phase. This is the braking phase, and then after some time you can see hovering, because we had two hoverings. Spacecraft will slow down and it will start seeing for the any hazards are there in the landing site. It will see and it will take a different, it will decide where I have to go and land. See, this is the first hovering phase, and then it has now decided that where it has to land, and then again second hovering phase is there. After that it will go and touch down. And this is post landing. This is only animation. It just shows after landing what and all happened. Like this is the rover ramp inside which rover was there. So once it comes out, it will get a solar panel opened, then communication from the lander antenna, then it will start moving. And this is the actual images from the lander camera, the movement of lander. And this was the moment where almost for 10 minutes we were crying inside the this one control center. The moment we saw Indian flag when rover is coming out, it was like nothing. It was the greatest ever experience for ISRO people. Okay, this is now government has called this as a Shiva Shakti point where lander has landed. Okay, and this is another good thing. Rover we could move for almost 100 meters within 10 days. This is second longest distance covered by any spacecraft on lander surface, because first is by China Chang'e 3. They have taken 6 months to cover 130 kilometers. We could cover 130 meters. We could cover 100 meters in 10 days. And it had automation, like when you can see it was moving towards a crater, then it has seen this crater and took a U-turn, and again it started moving here. Here one more crater was there, again it has come back. So it was moving, seeing any obstructions are there in the path. Okay, this conclusion. Okay, thank you very much.
So very, very interesting talk about an experiment which was a very successful mission for India, and most of you were recently coming out of that happy moments. Any questions related to thermal management in this particular area? We'll have 2 or 3 questions and then we have
Okay. Okay, I had the 3 questions, but I choose only one. Because otherwise- So, when you're doing the thermal simulations, how are you dealing with the heat pipes inside? Are you putting one element with high thermal conductivity, or you are really having a kind of model for the different orientation?
Yeah, this heat pipes, okay, for us it is not a new element. Till now more than 5,000 heat pipes are there in space from India. So initial times we have done extensive testing, and we established the H, the conductance factor from the heat pipe core to the panel surface. So that conduction factor only we are taking, and it comes to more than close to a lakh watts per meter square Kelvin is the conductance along the length of the heat pipe we get. Yeah. Yeah, we are creating elements along the length of the heat pipe, and we are creating a lumped mass, a node which we give H value to all the elements.
You see, this may be a very stupid question, because in the media everything is played. I was little surprised that I mean, you must have your assessment that it will not survive the lunar night. But you know, in the media it was there, it might revive this, that. In science, in engineering, there is nothing called might.
Yes.
You must have clear this thing that it will survive or it won't survive.
Yes.
So why was that uncertainty? Did anybody give any impression that it might survive, that then something has failed? Or it is designed for that and it has died, that's it.
No, sir, from beginning ISRO statements, if you see, all along we told its mission life is 14 Earth days.
Yes.
But public had more hopes on us than we had on ourselves. And really, if we had survived, Americans and Russians and Chinese would have gone wonderstruck how these people go. Really, science, as you said, none of the electronics packages will survive when they go below minus 50 or minus 60 degrees. Though we have done extensive testing, we have subjected rover, especially we have subjected to 100 Kelvin temperature. But see, there is a chance, it is a like a skill is involved. It may survive for one test, but it may not survive in the other test. So basically, and we ensured that all the electronic components are chosen such that in passive state, if it goes to 100 Kelvin and comes back to room temperature, it will work. But again, soldering joints, see, millions of interfaces will be there. We don't know where it will fail, and it has happened.
So one more question from anybody? Yeah.
So, thank you. The question is about the temperature under 2 centimeters, I think, or even 10 millimeters, that change 50 degrees.
Yes,
So there is a huge heat flux. Where is the heat flux coming from?
no, it is not a heat flux.
I didn't understand this point. I was ready to be surprised because really.
Yeah, we have seen almost 50 degrees Celsius difference in 100 millimeter.
Yeah.
It is see, heat flux is from sun only, because it was sunlit, the surface is sunlit, but for that heat flux, and we had in the probe heater also, we had a just I will show that.
I don't know what it is, but I don't know. No, it's under because it's below the surface. You see that? How much?
Yeah,
It's
see,
100 millimeters.
this is almost 100 millimeter. Surface temperature was around 10 degrees Celsius, but
It's a lot.
the 80th millimeter it was around minus 10. And the probe had a heater, and apart from that, it is like a thermal conductivity probe. So heater will be operated, and we measure the temperatures along the length of the probe. And apart from heater, we had an estimate of sun load in that region. We had modeled this.
Okay.
So what is the sun load falling on the surface, and then how much heat is going towards the probe.
So the thermal conductivity of this layer is very low.
It's of the order of 10 raised to, it is less than 1 into 10 raised to minus 3 watts per meter Kelvin. Very, very low. It is much lower than what we found in equator.
Wow. It's very interesting to know what is happening afterwards. No? But if it's continue like that,
Yeah. This we have taken multiple, all 14 days, even after because see, for doing hopping experiment we had to take back the instrument because it was deployed. So we have stored it back. Ramp was rover ramp was stored back. We have hopped, and after that again rover ramp was deployed again. This instrument again drilled. Then we have done the experiments. We got similar results. It is not local to that surface.
Okay, but I heard somewhere that this hopping experiment also helps in understanding whether the moon is hollow. So is that the case?
Okay, basically we had no doubt that it is not hollow, but only thing is we wanted data for lifting off from moon.
Okay.
Because it was only for a few seconds. See, for future sample return missions or coming back from moon to earth, we wanted to know what are the resistance, because we don't know the dust, what is the characteristic, how much this one force is required to lift off. The data we wanted for that experiment was done.
So I have some general question, since we are just concluding, maybe I get the benefit of being the moderator and ask the final question. So, of course there are two sub-questions. One is regarding the Chandrayaan. There are some people who say this is technically not in the South Pole, because the South Pole is usually beyond latitudes of 70 degree, and this is much lesser than that. So the reports that claiming that Chandrayaan mission was actually the first mission to go into the South Pole is not technically correct. That is my
No,
first
but,
question. The second one is why are the Indian the launches, the launch cost is much lesser. For example, either the Mangalyaan or the Chandrayaan, we always claim that our launch costs are fraction of what NASA and ESA do. So what is that brings the launch cost significantly lower than the other European missions? Because we are not compromising on the quality, and is it the fabrication cost, or what is it involved?
No, I'll answer both. The first answer to the first question is see, we never claimed that we'll land on South Pole. We only told we'll land near South Pole. See, you can see, and compared to any other, see, all other space agents till now landed near equator. We landed near South Pole, and we have next mission because see, this itself is great. See, the land characteristics as you move towards pole, you have lot of, because it's really challenging to land on poles. It is not like Earth. You have uneven surfaces, no? It is very high. The percentage of flat surface near the polar region, especially from 60 degree latitude onwards, no? It is very minimum. So we have to search the flat surface and we have to land. And the second thing is why all are behind South Pole landing is because of water ice craters. Because as you move towards the poles, sun load onto the crater deep inside will not be there, and we are assuming that water is there in the ice form. So anything you move away, towards the South Pole from 60 degree latitude is good enough. Okay. And second thing is we have next mission with the JAXA. Maybe it may fructify after now one more Japan mission is going on. There it is called Lupex mission. There will be further close to South Pole, but not South Pole. Maybe around 60. See, 90 degrees the latitude for South exact point. We landed close to 69.37 degree latitude. So there it will be 85 plus. And answer to second question is Indians should not ask this question. You know how much salary we get and how much material cost. So and how we work day and night. It's,
Yeah, but the
and
cost attached to these missions is enormous. I know ESA, I don't know NASA and so on, but the persons linked to the mission are really, I can say too many sometimes, and there is a check and a recheck and so on, something that is really takes a lot of time for nothing sometimes, no? So there is a waste of money.
and second thing is
Is it recorded?
see, I have told you fail cost. We used
Don't forget, you have to get projects from them.
Exactly. No, but
see, generally they reach a moon within say within 10 to 15 days because they carry huge fuel, huge engines, and they don't come around Earth several times. They start moving towards moon. But we have taken to reduce cost. We have taken because the entire spacecraft mass has reduced drastically because fuel mass has reduced. But we have taken the assistance of the gravity to propel further towards moon. This is other basic slingshot.
Slingshot method.
Because the subsequent Lunar mission from Russia must reach much
Yes.
faster than
Yes.
but of course.
Because we have time, they have money.
Yeah.
Now one more is launched 2 days back, right? American private mission.
That also failed. There is a leak in the propulsion system.
So we'll thank again.
Thank you.
So we will have to go for lunch. Before that, I request Mr. Marco Marango to hand over the nomenclature.
it's a good pleasure. Thank you.